ME407 Mechatronics Part 3 of Module 1. In this part we will be explaining you about the sensors and transducers. How you are going to differentiate between the sensors and transducer. Sensor, you have got a set of measuring parameters that can be displacement, temperature or pressure. Using a device or a conversion device, you are generating some useful signal like voltage, current, capacitance, etc. That is what a sensor does. Whereas a transducer is a device that converts one form of energy or signal into another form of energy or signal. So, transducer convert one form of energy or signal to another form of energy or signal. Commonly used measuring quantities are is stability showing. Left side it is what is the stimulus you want to measure and what is the quantity you are going to measure. So stimulus, acoustic, you can measure through wave, spectrum of the wave or velocity. Biological or chemical, you can measure through fluid concentration of the gas or the liquid. Electric can be measured through charge, voltage, current, electric field, conductivity, permittivity, etc. Magnetic can be measured through magnetic field, flux, permeability. Optical measurement can be with refractive index, reflectivity and absorption. Thermal measurement can be temperature, flux, specific heat, thermal conductivity. Mechanical measurement like motion can be position, velocity, acceleration, force, strain, stress, pressure, torque, etc. So, according to the type of measurement you want to make, there are sensors can be of different type. Depending upon the condition you want to measure and type of quantity you want to measure, different types of sensors are getting selected. So basically you can classify it to internal sensor or external sensor. Internal sensor can be further classified into position sensor, velocity sensor, acceleration sensor, force sensor. External sensors can be contact type or non-contact type. This internal sensors further can be classified into the position sensors can be encoder, LVDT, receivers, potentiometer, pneumatic position sensor. Velocity can be measured as tachometer, Hall effect sensor. Force sensor can be further classified into strain gauge, piezoelectric switches, micro switches. External type sensors in contact type comes in limit switch, slip, torque and touch sensors. Non-contact type can be range sensor, proximity sensor, ultrasonic sensor and laser sensors. What is the selection criteria of a sensor? It can be environmental factors, it can be economical factors, or it can be sensor characteristics. Environmental factors can be temperature range, humidity effect, corrosion, size, overrange protection, susceptibility to EM interference, ruggedness, power consumption, self-test capability. Economic factors can be cost, availability and lifetime. Sensor characteristics can be further divided as sensitivity, range, stability, repeatability, linearity, error, response time, frequency response, etc. Different type of position sensor popularly used are potentiometer, LVDT and encoders. This potentiometer can be of two types, either it can be linear or rotary potentiometer. In rotary type, as you can see, as we rotate, the resistance change is happening, the wiper is keep on moving from one position to the other and through terminal you are monitoring what is the resistance that is happening. That is what the rotary potentiometer does. In a linear potentiometer, this is what the schematic. We can see this motion we can detected by this linear, this wiper movement is happening along this direction, and according to the wiper position you can monitor the linear position of this element. Different type of potentiometers that is popularly used. It is a inside potentiometer. It is a preset potentiometer. It's a general. Common example for this type of potentiometer can be a regulator in a fan, what popularly used in household applications. In a potentiometer sensor, how the linear displacement is measured or converted to rotary movement to measure the resistance here. So this is the linear movement. It is the direction of rotation is here, and it is acting against the coil spring, and this linear movement is translated into the rotary movement, and here you are going to measure the resistance in the resistive strip. Continue from the previous slide. This is how the measurement is taking place from the resistive strip in a rotary potentiometer. We can see a wiper here, resistive wire, mandrel on which this resistive wire you are winding up. So this angular displacement can be measured through the resistance here. Voltage is monitored here. LVDT or linear variable differential transformer. LVDT is a transducer for measuring linear displacement. Normally excitation is by AC signal to induce a AC response on a secondary. The core position can be determined by measuring the secondary response. This is the instrument, different types of instrument, LVDT. This is the construction details of a LVDT. Basically being used for linear displacement measurement, displacement in direction. It has have two type of coil, primary coil and a secondary coil. There are two secondary coils and one primary coil. It is wound around a hollow cylinder. Continue from the previous slide. LVDT, the construction. Physically it looks like this. It has got a primary coil and two secondary coils. Two secondary coils. Looks like here. Two secondary coils and a primary coil. So a iron rod is moving. This movement of this rod is measured because this is how it is being happening, and you can see how the output in different coils it is coming. Red shows the primary coil, blue and green shows the secondary coil. How the working of LVDT is happening. This is the winding, primary winding and secondary winding. So what happens is, if you are giving a supply to the primary coil, current flows through the coil, creating a varying magnetic field in it. This magnetic field interacts with the secondary coil. It will produce a magnetic field that will interact with the two secondary coils, producing an EMF in both of the coil. Then, if this iron core, this is iron core, is moving in either direction, an EMF is produced, in both the coils, and if it is moving either in this direction or this direction, EMF difference will occur in secondary coil ES1 and ES2. So if it is a center, there is no EMF difference. If this center core is moving either direction, there will be an induced EMF difference will be happening between ES1 and ES2. So the position of the iron core considered is decide how much movement it is happening. So if it is moving either direction, EMF change will happen between ES1 and ES2. This change is getting monitored. So this is how the core displacement. If it is moving in the left, EMF difference is shown here. Right also it is showing the EMF difference between the secondary and primary, two secondary coils. Some of the applications of LVDT, displacement monitoring, that is extensometers, temperature transducers, butterfly valve control, servo valve displacement sensing, and again precision gap between torch and surface of the welding in a welding area can be monitored through LVDT. Second area of application, deflection of beams, strings and rings, as load cell, force transducers and pressure transducers. Thickness variation of workpiece dimension gauges, thickness, surface irregularities and profile measurements, product sorting by the size. Another application is fluid area, fluid level and fluid flow measurement, position sensing in hydraulic cylinders. Another application area is velocity and acceleration of automotive, suspension and control, etc. General classification of encoders. Digital optical encoders can be classified into basically two categories: absolute digital optical encoder or incremental digital optical encoder.
What is an encoder? An encoder is a communication device that controls the motion of an operating device. Encoders are used to translate rotary or linear motion into a digital signal, helping to determine the speed or position of a motor or other moving equipment. Basically, an encoder acts as a measuring system for moving parts. There are two different types of encoders: linear and rotary. A linear encoder responds to motion along a path, while a rotary encoder responds to rotational motion. Within these two categories, we can list different encoder measurements types such as absolute encoders, which are capable of providing unique position values from the moment they are switched on, and incremental encoders that instead generate an output signal each time the shaft rotates a certain amount. Encoders also differ in electromechanical technologies such as optical, magnetic, inductive, capacitive, and laser. In this video we will focus on the most popular encoder technology, the optical encoder. We will see different types of optical encoders and their applications. Let's start from the linear encoder, which is basically a transducer paired with a scale that encodes position. The transducer reads the scale in order to convert the encoded position into a digital or analog signal, which can then be decoded into position by a motion controller. It is normally used for linear measurements in order to detect the translational motion of an object. These encoders in fact can use a rod or a cable that is run between the encoder's transducer and the object that will be measured for movement. Let's move on to the rotary encoder, also known as shaft encoder. Unlike the linear encoder, the rotary encoder collects data and provides feedback based on the rotation of an object, or in other words, a rotating device. Since it converts the angular position or motion of its shaft to analog or digital output signals. Basically, both linear and rotary encoders do the same thing. They produce an electrical signal. When this signal is properly processed by the electronic circuits, it produces analog or digital output signals, which are translated into angular movements, linear and rotational motion, as well as in rotation speed and accelerations. More than 10 years in industrial supplies have led JAIS to become a qualified partner for some of the most important industrial automation companies, offering a wide range of different encoders types. As we have said before, both linear and rotary encoders can perform absolute or incremental measurements. Absolute rotary encoders can measure angular positions, while incremental encoders can measure things such as distance, speed, and position. Here, an example of absolute rotary encoder. We can see inside that a slotted disc on a shaft is used in conjunction with a stationary pickup device. When the shaft rotates, the disc is rotated in a beam of light, such as an LED, and the markings on the disc act as shutters, blocking and unblocking the light. Thanks to this, a unique code pattern is produced. This means that each position of the shaft has a pattern, and this pattern is used to determine the exact position. If the power to the encoder was lost and the shaft was rotated, when power is resumed, the encoder will record the absolute position as demonstrated by the unique pattern transmitted by the disc and received by the pickup device. Absolute measurement encoders can be single-turn or multi-turn. Single-turn absolute encoders are used for measurements of short distance, while multi-turn absolute encoders would be more suitable for longer distances or more complex positioning requirements. Incremental rotary encoders create an output signal every time that the shaft rotates a certain amount. This output signal is then interpreted based on the number of signals per revolution. This encoder begins its count at 0 when powered on, so there are no safeguards regarding the position. That's because, unlike the absolute encoder, the incremental encoder begins its count at 0 in startup or power disruption. For this reason, it is necessary to determine a reference point for all tasks requiring positioning. The most common type of incremental encoder uses two output channels, A and B, to sense position and direction of rotation. Using two code tracks with sectors positioned 90 degrees out of phase, the two output channels of the encoder indicate both position and direction of rotation. If A leads B, for example, the disc is rotating in a clockwise direction. If B leads A, then the disc is rotating in a counterclockwise direction. Some types of incremental encoders with integrated communication signals are normally used as motor feedback. These additional signals simulate the Hall phases, which are usually employed in brushless motor, as you can see in our previous video. Linear encoders, on the other hand, can be used inside a milling machine in order to obtain direct control over the exact position of the material. We can find encoders in many robotic devices for multi-axis synchronization control, but also we can find them in common printers. Absolute encoders can be used inside the pitch control system of wind turbines, allowing the blade's angle to be adjusted according to wind speed. An absolute encoder is often the preferred solution when the device is inactive for a long period of time or moves at a very slow rate, such as fluid gate control. Due to their many advantages, optical encoders are used in many industrial sectors, specifically where high precision is most needed, like in the healthcare sector, where this type of encoder can be used for precision medical equipment. If you found this video useful, please let us know by leaving a like and a comment. You can also share it, and don't forget to subscribe to our YouTube channel. Find out our next project by visiting jaiscompany.com.
main parts of the encoder can be, there are 4 parts: a light source, a code disk, light detector, and a signal conditioner. So another classification of encoders can be linear or rotary type. Rotary type or linear type encoders can be further classified into incremental and absolute encoder. This is the working of a incremental type encoder. A LED light produces the light source. It will be falling on a rotating disc, a marked disc, and there are perforations around this disc. Some angle light will be permitted through this, some angle it may not. So whatever light passing through this will be falling on a photosensor. With this light falling on the photosensor, the sensing, we can identify what is the speed at which this disc is rotating. Some place it will permit the light, some rotation angle it may not. From this we can identify at what speed this disc is rotating, or we can measure the angular displacement of this disc. This is the basic working principle of a incremental type encoder. What I was trying to explain in the previous slide is once again explained here, the working of a digital optical encoder. Here we can see a rotating encoder disk, and you can see a LED light source. That light will be coming from here and passing through this rotating disc, and it is compared against a stationary mask, and you can see the photo detector here. The light will passing through this will be falling on this photo detector. So we can compare the rotation of this rotating disc with the stationary mask disc. This comparison will give what is the rotation angle or rotation speed of this rotary disc. The same thing is shown here. Here further the working can be explained. You can see there are two sensors, two sensor positions, and have a reference slot and a slot at home. This is for referencing, and this is for the actual rotation is measured using sensors in this. The encoder disk of an incremental encoder consists of one track and two sensors. One track, it is having one track and having two sensors. This is a one track and two sensors it is having. The output of this encoder is shown below. Channel, it is because there are two encoders, it is having two channels, channel A and B. When the shaft rotates, the pulse trains occurs on these channels with a frequency proportional to the rotational speed. You can see the pulse channel, that is pulse train that is happening with the two channels, channel A and channel B. You can see there is a difference. The waves are formed at, there you can see a 90-degree shift, phase shift. 90-degree phase shift is there. Further, these signals are fed to a comparator which determines the magnitude and sign of the error. And this is the working of an incremental encoder. These incremental encoders provide more resolution at lower cost compared to the absolute encoder. you have having a price advantage compared with the absolute encoder. It is comparatively cheaper. This is how physically it looks like, this incremental encoder. It is having a rotating disc and you have got a sensor on the top of it, and this is how pulse, two channels, two encoders, two pulses are pulse channels are generated at 90-degree shift. This is how A and B pulse channel, here we can see, it is generated on the fixed sensors. This is a picture of a linear encoder, linear incremental encoder. Elements are the same except in rotary encoder the movement is in rotation, whereas here it is a linear movement. Otherwise all the elements are what we used in a rotary encoder is same for the linear encoder. You have got a linear scale. Scale is linear instead of rotation. So you are having a LED light, a condensing light, a scanning disc, and whatever through the perforation on the scale it will be falling on a photovoltaic cell. And here the dimension of this opening is given as 60 micron. So this scale is perforated. Whatever light that is falling through the perforation will be falling on the photovoltaic cell, and as either scale is moving or all this equipment will be moving, normally scale will be moving, accordingly light falling it will be sensing. Whatever I am trying to explain in the previous slide is represented here as a schematic of the incremental linear encoder. It is having a light source and a light sensitive cell is here, light sensitive cell. So from the light source through the condensing cell a glass scale. Through the glass scale it will be falling on the light sensitive cell. This is how the schematic arrangement for a incremental linear encoder. Here working of an encoder with the help of a CNC machine tool is explained in this figure. Here you can see you have to position this machine tool X or Y axis to some position. Here we are, this axis you have to, this machine tool element has to be placed. For that you are making use of this servo motor. As whichever required movement, servo motor will rotate, and this will make, servo motor rotation will make the rotation of the lead screw. To the machine tool is connected its nut of this lead screw. As this is rotating, it is converted to nut linear movement. That is how the movement of the rotary movement of the servo motor is converted to the linear movement of the machine tool. Okay, you are giving a required movement from the servo motor through machine control command. You have to ensure whatever command you have shoot out or asked for, the required movement has been okay. For that, checking that, you are using the encoder. Getting a feedback, you are using encoder. So once you are making servo motor rotation and making a required movement the tool axis, to ensure that the required movement is achieved, you are using a encoder. Here we are showing a linear encoder. So this linear encoder, this rotate along with the lead screw, the rotation, and you are ensuring that required rotation has been happened to this lead screw, making this machine tool axis to move in a required linear movement. So this feedback arrangement is through this rotary encoder here. The same thing, if you are going to use it a linear encoder will be fixed somewhere here, and that will be moving around with this machine tool axis. That way also you can do it. Here it is shown a linear encoder, rotary encoder. The same thing we can make sure using a linear encoder also. This is a demonstration of the rotary absolute encoder. Absolute rotary encoder. So here you can see there are number of perforations are more because you want to monitor each position will have a unique identity around this disk. To ensure that only we are having a large number of perforations that is happening in a absolute type of encoder compared with the incremental type encoder. As you can see, incremental encoder, this number of perforations are less. Here, each position along the disk will have a unique identity. If you take a cutting here, unique identity will be there. So otherwise, all the other elements looks similar to incremental encoder. It is having a light source, a condensing lens, graduating disk, and a photovoltaic cell. Whatever light that is falling through this will be collected using a photovoltaic cell. So this is how the construction of an absolute encoder. So absolute encoder disk, how it looks like, you can see the actual disk will looks like this. So each cross section will have a unique identity along its rotary along this 360 degree, any 1 degree or any degree you take, it will have a uniqueness. That is what it is ensuring. And you can see there are number of tracks will be more to ensure. So you can see here 4 bits are shown. So each position will have a unique identity for identifying the absolute encoder rotation. So here the absolute encoder, what is the difference between an incremental encoder is explained here. Absolute encoder have an encoder disk, that is floating mark order slots on a power transmission shaft and a stationary pickup, but the disk mark output a unique code for each shaft position. Absolute encoders are either single turn or multi-turn encoders. What is the difference between a single turn and a multi-turn? Single turn absolute encoder can verify position within a single turn of the encoder shaft. This makes them useful for short travel. So single turn is useful for the shorter travel situation. In contrast, multi-turn is useful for the more complex long position situation. So single turn, once again repeat, single turn absolute encoder can verify the position within a single turn of the encoder shaft. Whereas long travel, you are going for a long position travel or situation, you are going for a multi-turn encoder.